Now, but lithium is kind of different in the group 1 elements. And why is it different? Because you can see lithium has a very small structure, right? And then looking at the nucleus of lithium, the nucleus contains dense positive charges. And the same thing applies to all other elements in the periodic table. Their atoms contain dense positive charges at the center or in their nucleus. So what that means is the force of attraction, you know, these X's or these crosses are electrons. So if you have lithium with dense positive charges, let's take this as the nucleus of lithium with positive charges, dense positive charges, right? And then just on these positive charges, you have electrons, 2 electrons on the first shell, and the third electron, because lithium has 3 electrons, 2, 1, right? The force of attraction these electrons are experiencing towards the nucleus is so great that lithium would not want to lose its 1 electron, right? So this concept was explained to us by the Frajan's rule. And Frajan's rule is concerned about atoms, elements with very small atoms. That when you have a very small atom, there is a net positive charge generated by the nucleus, and the electrons themselves are negative. Positive and negative charges would want to attract. And the attraction will be so much that the nucleus won't allow for that atom to lose an electron, right? But if you bypass lithium in the case of group 1, and you move to other atoms like sodium, potassium, rubidium, cesium, and francium, which have an appreciably large amount or large size, then our concept holds for this, that sodium ordinarily will lose its 1 electron to attain a stable duplet. Why? Because it has a relatively larger size compared to lithium. So the outermost electron of sodium will experience only little amount of force. Why? Because the nucleus of lithium, of course, like every other atom, is positively charged. And then you have the greatest amount of force experienced between these 2 electrons because they're the closest to the nucleus. Hence, they experience the greatest amount of force. And which other electrons experience appreciably large amount of forces? These electrons. So these electrons also, because they're sort of closer to the nucleus, also experience a great deal of force, but lesser than this in the first case, right? What about this outermost electron? It is so far from the nucleus that it experiences lesser amount of force compared to the other electrons. And then what happens? Because the force of attraction experienced between this electron and this nucleus is small, the atom can afford to lose that electron. So Frajan's rule does not apply to this atom, right? So sodium can lose that outermost electron to form a positively charged ion. That makes sense. Now, why is it that the electrons closer to the nucleus experience a greater amount of force than the electron farther from the nucleus? Now, this concept is explained by screening effect. A screening effect, or you call it the shielding effect. We talked about this in chemical bonding. Now, what is screening effect and what is shielding effect? Screening effect or shielding effect is the shielding or the blocking of distant electrons from the nucleus by inner positioned energy levels. So here you have a nucleus, let's put it as N. Here you have an outermost electron, right? There are some energy levels here, all right, that shield these outermost electrons. They block the outermost electrons from receiving full force of attraction from the nucleus, all right? So because those energy levels block this outermost electron from receiving full force of attraction, the force of attraction there is weak and can easily be broken. That is why metals or elements like this can afford to lose electrons. And now this point says that they ionize by loss of 1 valence electron to form a unipositively charged ion. Let's see how that is possible. So for sodium is an exception, we said that, with configuration 1s2, 2s2, 2p6, and 3s1. Sodium can lose that one outermost electron, right? Because this one outermost electron has been shielded by all these energy levels. Hence, it receives only very little amount of force from the nucleus of sodium. And upon losing that electron, what happens? It becomes sodium ion, a unipositively charged ion. So sodium atom can lose an electron, right? Okay, let's make us understand. Sodium atom can lose an electron, right? To give us what? Sodium ion. And the ion will be in solution. What does this mean? It means that once an electron is lost from sodium, it becomes an ion, which is a cation. Rearranging this equation, we have sodium atom bringing the electron to the other side, gives us sodium ion plus an electron. And that's the equation. So group 1 elements lose an electron to form a uni, means 1, positively charged ion. What about potassium? Potassium has atomic number of 19. 1s2, 2s2, 2p6, 3s2, 3p6, and 4s1. This outermost electron would have been blocked by all these energy levels. Hence, that outermost electron receives only a negligible amount of force from the nucleus. Hence, it can easily be lost. And then when you lose that one electron from an atom of potassium, what happens? It becomes a unipositively charged ion. So potassium K solid will lose an electron to form potassium ion, right? Which is a unipositively charged ion. So in this lecture, we talked about 3 properties. Number 1, we talked about action on water to produce an alkali and liberate hydrogen gas. Number 2, we talked about them having one valence electron, all of them having one valence electron. And number 3, we talked about these atoms losing an electron to form a unipositively charged ion. There's still a couple more chemical properties we'll talk about in the next lecture. So let's take a pause here for this lecture and join us in the next lecture when we'll continue our lecture on chemical properties of group 1 elements. So guys, thanks for sticking with us, and we'll see you in our next lecture where we'll continue with this